Welcome back to ECE 340. 4 more lectures. Apparently that means we'll have maybe 2 students left by the end of the semester if we keep falling off at the rate that we're falling off. Maybe after last exam they didn't think they needed to come again, but the final might be a wake-up call relative to what we just experienced in exam number 3. Before this semester ends, you have 3 more things to focus on. 2 homework assignments, homeworks 9 and 10. Homework 9 is due in a week. Homework 10 is due the next class period. Your final exam is 3 weeks from yesterday, I believe, is one way of thinking of it. So 20 days from now, you have your final exam. It's on a Wednesday from 1 to 3. Today, hopefully you came prepared to watch a movie. You did. Oh, and without popcorn. Well, you'll have to try to stay awake. That's the main thing that I'm wanting you to focus on. I'm going to be sliding through a lot of material in order to essentially get us comfortable with understanding the last sort of main concept. We'll talk about sampling, but that's maybe not as critical as the Fourier transform. This pair of relationships, the analysis equation, essentially what's the frequency content in a aperiodic or non-periodic waveform, little x of t, that's collected in this expression, capital X of omega, that gives you the frequency content in x of t. That's a way to go between time domain and frequency domain. The synthesis equation says how do you create a signal in the time domain out of different frequency information. And you might see this referred to as the Fourier integral. These are now in chapter 7 in equation 8 of that chapter. To get there, what I want to do today is actually pick up with chapter 6 material that we hopefully are very comfortable with, periodic waveforms, and see what happens to the line spectra, see what happens to the frequency domain content of a signal when we have a signal that's this periodic train of pulses and we adjust either the period or the pulse width. And we aren't going to do it simultaneously. We'll keep one of those parameters fixed and adjust the other one and see what we can learn or what insight we can collect from that particular set of scenarios or examples. We will then derive in a sort of more intuitive fashion the Fourier transforms that I just showed you. So I'm trying to get you comfortable with those 2 pairs. We'll derive that transform pair, then we will start using that. And the first thing that we'll do is we'll simply say, oh, let's look at finding the frequency content in a pulse. And then we'll start looking at more additional signals x of t that we're familiar with in terms of cosines, exponentials, etc. And what do their Fourier transforms look like? That's where we're headed. And as I said, the end of the semester, we will hopefully get to sampling so that you can understand if somebody starts talking about sampling, Nyquist rate, what happens if we don't sample at the Nyquist rate, what does it mean to have aliased frequencies, what is that, what's that concept, and that's where I would like to conclude the semester. Here's what I want to start with today, chapter 6 type material. This is what I left you with last time. I think that was your homework assignment for last time. For today was to derive these capital D sub n's, these weightings on, if this is a period, whoops, to make this more accurate, I should say, that's going on and on for all time in both directions. That's now a periodic waveform. It has a period of capital T, units of time, and the width of the pulse, I'm using this parameter little d, to determine what the width of the pulse is. What I want to do is look at a couple of scenarios. One is what happens when I make this period longer, when I spread these pulses out. The second scenario is what if I keep the period the same, but now I adjust that pulse width within that period and make it wider? What's going to happen to the frequency content of those two scenarios relative to this basic case? Is this the answer that you obtained? These are the D's. We derived D sub 0, the average value. That was the height, A, times the width, D, and divide it by the period, capital T. That we feel comfortable with. That seems to make sense by remembering what that pulse train looks like. It has an average value of AD over T. Then, did you derive this for the different weightings on the various harmonics? If I gave you a capital T, the period, then you could compute omega naught. That's the fundamental frequency. And now you know what all the harmonics will be at. They will be at integer multiples of that harmonic, or I'm sorry, of that fundamental frequency. This now says, well, we have something that looks like sine x over x in terms of the shape of the d sub n's. What's the amplitude of this last term, this e to the minus j? 1. So that's not really impacting the amplitude. If we wanted to know what's the frequency content in the various harmonics, the first harmonic would be capital D sub 1. We have our average value, AD over 2, weighted by this, what we will learn today is a sinc function. It's not in the restroom or the kitchen. It's not the kitchen sink function, but it's the sinc function, SINC. We'll learn what that is, but that's now sine of x over x, and that has a particular shape, and you'll want to get very comfortable with that sine x over x behavior. Let me, like I said we'll be at the movies today, and maybe you didn't remember to bring your popcorn, but let's quickly scroll through this derivation. I'm maybe guessing that not all of you worked through that between Tuesday and Thursday, and I'm assuming that's not a bad guess. Am I wrong? Sometimes I'm not wrong, actually. Here's the average value. That was the AD over T. That one's pretty straightforward. But this derivation is, I think, helpful in figuring out where some of these formulas or relationships come from. Where did that sine x over x behavior come from? Here is D, capital D sub n for n not equal to 0. By definition, that's just x of t weighted by this complex exponential divided by the time, and we're integrating over one period. In this case, our one period that has any non-zero content is only between 0 and a little d. If we integrate this, the a is constant, it slides out, and the only thing we really have to worry about is integrating a complex exponential. And integrating an exponential, all we do is really sort of divide by what's not multiplying the dependent variable t in the integrand, and then remembering to write down e to the minus jn omega naught t. We can evaluate that at the upper and lower limits, and that's what I've done in the third line that's on the board right now. Questions on that? That should be okay. That's not that difficult, although I've had some faculty say, well, they don't know how to integrate an exponential. Yes, they do. They maybe just forgot. Okay? So, now you haven't forgotten. Now you know what this is. What we want to do now is just some algebra, some playing with this, and that's what I want you to start to get comfortable with. I'm going to slide over a little to the right because you know what it's equal to. It's equal to capital D sub n. The very first thing that I did was I pushed that minus sign in to the square bracketed expression. And now I have 1 minus e to the minus j n omega naught d. This is in a typical form that is screaming at us, oh, maybe I can identify a sine or a cosine from that. The way to do it is to realize that let's just sort of split the difference between a constant and this e to the minus j n omega naught d. Meaning let's factor out half of this from both terms. Half of this is e to the minus j n omega naught d over 2. So I'm going to factor that out. And if I want to get that 1 back, then I have to multiply it by the positive exponent piece. Meaning, from this square bracketed to these next 2 terms, is it clear where that's coming from? I'm just factoring out a half of the e to the minus x piece. So I'm factoring out an e to the minus x over 2 from both pieces. That's all I've done in this step. Now what I want to do is put that j underneath those 2 complex exponential terms and scale by 1. I can always scale by 1, and in this case my 1 is 2 over 2. That gives me this 2 in the denominator, and that's what I wanted to make this look like the Euler form of the sinusoid that I want. This is now e to the jx minus e to the minus jx over 2j. And that's then this sine expression. I'm also, in order to get this d to appear downstairs, I'm going to put a d upstairs. I'm going to again multiply by 1, except this time my 1 is d over d. And I'm going to rewrite 2 as 1 over 2. And that 2 now pops down below. Now I have this common factor of n omega naught d over 2 factored outside in the denominator, and it's in the exponent, and it's in the sine expression that I've now been able to identify in about the middle of the page or middle of the screen in this derivation. Are we following this process? Hopefully you don't have to write it down. You can just look at this again or print it out or store it however you want to do it. This n omega naught d over 2, I'm going to slide underneath the sine. And now I have this sine x over x expression. And I said that's what we are going to just call the sinc function, the SINC of x function. Here's the sort of the phase weighting term, and here's my average value piece, the AD over T. So this is the average value weighted by a sine function and raised to this e to the minus jx value. Questions on that? And that's actually the expression. There's the sinc with omega naught being equal to 2 pi f naught, which is 2 pi over capital T. And I wanted you to always remember that until you retire from your day job. And maybe even after, before, you can remember it for your night job. Omega naught is 2 pi f naught. That's now capital D sub n. Now let's look at that relative to a couple of, well, let's look at what D sub n is doing. That's this frequency content of this pulse train. And it's actually going to sort of go like this. It's going to go like the sine, but it's going to have a 1 over x behavior to it. So it's going to roll off as you get higher in frequency, and it's still going to be going up and down as it goes out to infinity. That's the sinc function. We would like to know, when is it going to first go through that zero crossing? And that's what I'm explaining here. The sinc function is sine x over x, which has a value of 1 at 0 at DC, sine x over x, L'Hopital's rule. So we want to know, when does the sine of n omega naught d over 2 equal 0 the next time? It's when any integer multiple of pi. And we would like to know maybe when it does the first time. So this is after n equals 0, all we need is that sine to be equal to 0, which means that the argument needs to be a multiple of pi. If we work through an example, suppose that we have this pulse train that's has a 1 second period. Capital T is 1 second. The frequency now is 1 hertz. And now if I could, if I could lengthen that, the duration would be the d, wouldn't it? If I could make that last longer, that snap, the length of that sound would be little d, and in between, I'm saying that's every second. Yes? So now the duty cycle is little d over capital T. And in this case, what is our duty cycle? Our duty cycle here would be 10% in this example. It's on 10% of the time. We're saying, just to get a feel for what's going on, let's say that the period of this is 1 second, this pulse train. It lasts, each time it comes on, the pulse width is 100 milliseconds, or 1/10 of a second. Now, when is it going to, in terms of the frequency domain, when is it first going to go through 0? At what value of n? Where's the first 0 crossing? And so we can set this expression, which maybe I've scrolled beyond, but up above, we want to know, when does 2 pi over omega naught d times 1, what's that n value? If capital T is 1, omega naught is just 2 pi. Omega naught is now 2 pi. We have 2 pi over omega naught. We have 2 pi over 2 pi. Those cancel, and now we are dividing by 1/10, or essentially we are obtaining for our n value. And what was little n? What did that represent? That's the harmonic. That was capital D sub little n. That's the harmonic. This is saying that if you had a 1 second pulse train with a duty cycle of 10%, most of your frequency content is going to be occurring between DC and the 10th harmonic. And what's the fundamental frequency? In terms of radians per second, it was 2 pi. But in terms of maybe what we're used to thinking, cycles per second, or in hertz, it's 1 over t, and t was 1, meaning for a 1 hertz periodic pulse train, the 10th harmonic is just 10 times 1, or 10 hertz. So most of our frequency content in this pulse train that has a period of 1 second with a duty cycle of 10%, so that period, or that pulse, is lasting 1/10 of a second. And it gives us frequency content essentially out to 10 hertz. So there's sort of a reciprocal nature, a reciprocal concept going on here. A 1/10 of a second duration pulse width yields a 10 hertz zero crossing. That's where the majority of the frequency content lives or belongs. Let's look at these two scenarios. Now that we have this expression, capital D sub n, for this pulse train, we can now, in that capital D sub n, we could change little d and capital T. The first case, we want to lengthen t and keep the pulse width constant. The second scenario, we want to lengthen the pulse width but keep t at 1 second and see what happens. And what we want to do then is examine the amplitude spectra in both cases. Scenario 1 is as follows. Can you guys see that if I reduce it? Is that still legible? You have young eyes. Here's scenario 1. We want to increase the period. So we're trying to now see what happens if we make capital T bigger. We started with it being 1 second. But here's our relationship between the period of our waveform and the fundamental frequency omega naught. If we increase capital T, we're dividing by capital T in our formula for omega naught. That means that omega naught, if you think about what that represents the spacing between your lines in your frequency space. Omega naught, 2 omega naught, 3 omega naught. Now if we increase capital T, if we make our pulses happen less and less frequently, then what happens to omega naught? It's going to decrease, isn't it? So now our spacing between those lines in our line spectra are going to be closer together. With omega naught smaller, these spectral lines become more and more dense as we make capital T wider and wider, or we lengthen the time between those pulses. D, remember, is fixed. We didn't change. It's still on for 1/10 of a second. It's now I'm sure that was periodic. Don't time me. Don't hold me to that. But now that's the behavior that we have. We have more time between that pulse. I'm sorry? So now what is that going to do? If D is now fixed, then the first null, maybe effectively we haven't moved that zero crossing. We're going to have more harmonics, but we really haven't moved that zero crossing where it first crosses 0. So the effective bandwidth has not changed by keeping D, our pulse width. It's still 1/10 of a second. So the effective frequencies that are present should still be around 10 hertz. That's the frequency content that we have working. And here is a picture of that, a MATLAB type picture. Here's the impact of increasing the period, capital T. The top, so the left pictures are the time domain waveforms. The right column is what's happening in the frequency domain. Maybe I should does this give you a better, maybe not. Here in the top row, it's 1 second intervals. That's our period. In the bottom row, I've simply doubled that. I've made our pulses every 2 seconds. And what happened to our lines in the frequency space? Now they have become more dense, haven't they? But if we look at when they both cross for the first time, 0 in magnitude, that's still at the same frequency. Even though we have many, many, many more lines, those lines are denser, we still have essentially the same frequency content, out to 62.8 radians per second, and that's 10 hertz. Questions on that? That's what this is trying to say. Here we've kept D, our duty cycle, or sorry, the width of our pulse, the duty cycle is now changed. It's now in the bottom path, it's 0.1 over 2, and here it's 0.1 over 1. But the width of that pulse hasn't changed. It's still a tenth of a second. We now have denser lines in our spectral content. And what I'm wanting you to start thinking about is, what if we let the period get ever bigger? As we let the period get bigger, what happens to these lines? They just get closer and closer and closer together, don't they? And eventually we're going to get all frequencies in the limit. And we'll quit representing that as line spectra, and we'll just view it as a continuous spectrum. Let's look now at what happens in the second scenario, where we increase the pulse width while keeping the period the same. If we keep the period the same, then omega naught is fixed. But now we're making D bigger. If we make D bigger, that sine function's argument is going to increase, isn't it? Sooner. So we are going to change when we cross through 0. It's going to occur sooner in frequency or in harmonic content. We're reducing the width of the line spectra envelope. Not necessarily the spacing of those lines, but the time where they fall off, how quickly they fall off. The first null is going to occur sooner in frequency. And that's going to then lower our effective signal bandwidth. This is what I'm trying to say. Notice that these pulses are happening exactly at the same width from each other. Capital T is remaining constant at 1. Our period is 1 second. But in the bottom half of this display, it's now 4 times as wide, our pulse width. And here's sort of a little aside. In omega naught D over 2, the first time that's going to go through 0 is when it equals pi. If we solve that for little n, what harmonic is going to be where we cross 0, then this calculation shows that it's 1 over 0.4, or 2.5. The first null, then, for this wider pulse width is occurring between 2 and the second and the third harmonics. And that's 2.5. And that's 2.5 hertz in this case, which is now 1/4 of 62.8, or at 15.7 radians per second. And that's because we made this duration of our pulse wider. So it's essentially lower frequency content. If I gave you a really wide pulse width, you would say, oh, the frequency content is pretty low. If I continued to shrink that pulse width, you would say, oh, the frequency content of that signal is getting higher and higher. And now you may be concerned with that, because if you now have a pulse width that's 1/millionth of a second, now you know what your system has to do in terms of frequencies that it needs to be able to process. Yes. Now, what's going to happen? The question was, what if we make this duty cycle become closer and closer to 1? What's going to I think, what's going to happen? If I made my duty cycle 1, what do I have? It's on all the time, isn't it? And what's a signal that's on all the time and it's constant? It's DC. What frequency is present at DC? 0. So you would expect to have all of your content now localized or right at 0, and that's what we'll find with the Fourier transform. We'll have this impulse right at DC or at 0. We won't have any other frequencies present. Does that make sense or help? Here's the main point. As we make that period of time, or our period of that periodic waveform, as we increase it, as it gets longer, then in the frequency space, those spectral lines are going to get closer and closer to one another. In a formula sense, we know that omega naught is 2 pi over capital T. And capital T is increasing. That means that this fundamental frequency is decreasing. And what happens in the limit? We can think of this in 2 different spaces or domains. In the time domain, as t goes to infinity, we're never going to repeat that waveform. If we're not repeating, then we're not periodic. It becomes a non-periodic waveform as capital T goes to infinity. Is that clear? If we just put a blip and that's it, what we want to be able to do is figure out what's the frequency content in that blip so that we know how our signal or our circuit has to behave frequency-wise. Is it favorable to those frequencies? Is it really messing them up? And if it is, can we accommodate that? In the frequency domain, then our spectral lines, as the period goes to infinity, then the lines are basically going to be right on top of each other, infinitesimally closer and closer, so that now they become, it's just a continuous waveform and it's not worrying about lines. The spectral content now is dense if we're dealing with one-time event signals. Questions on that movie? What was its rating? It needs to be PG-13 or, well, anyway, the person that asked what kind of radio I listen to, but last night they were talking about ratings of movies. And PG-13, I guess, grosses the most in terms of revenue, even though maybe it only represents 10% of the content of the movies that are out there. But that's the sweet spot. This presentation hopefully was not PG-13, I don't believe. May have been G, right? Do I have my movie? Pardon? So this was not PG-13. And what we want to do is learn now a little bit more about this Fourier transform. And this is, whoa, what am I doing? I'm not being truthful here. We're now in chapter 7. This is chapter 7. We're in section 7.1. And these are the two equations that we want to understand sort of where they're coming from. How can we obtain those based on what we've already learned or what we've done in the past? Let's look at deriving these relationships so that we get comfortable with what's going on. And what is happening here? The first one is really telling us the frequency content of your signal x of t. You are taking x of t, some waveform, and let's just pick a frequency. Let's say you want to know how much frequency content do I have at omega equal 10 radians per second. You could plug in omega equal to 10. And then you would take that x of t and you'd say, okay, I'm trying to see how strongly correlated x of t is to sines and cosines at 10 radians per second, because I'm integrating over the entire time history of x of t. So whatever x of t looks like, I'm trying to say, how does that look like 10 radians per second? And this will tell me with a complex number, but we could take its magnitude and get a feel for its magnitude. This tells us then the frequency content. This is the analysis equation. We take our signal x of t and we weight it by spinning sinusoids, complex exponentials, and that will give us the frequency content in that signal x of t. And now x of t is not periodic in most of the cases. We actually will want to find the Fourier transforms for some special signals, and we'll try to do that. The second equation is more like what we've just concluded when we said, oh, let's write x of t as a sum of sines and cosines. And that's really what you're doing here. You're saying, oh, here is the frequency content of your signal, capital X of omega. Let's synthesize x of t. We simply weight capital X of omega, the frequency content, by this sinusoidal variation, which varies with all frequencies omega between 0, DC, and infinity. And we're going in both directions. We want to include plus and minus frequencies. That's what little x of t is. This is analysis, this is synthesis. And we need those pairs because we want to be able to go back and forth between the two domains. We want this so that we want to know what's the frequency content in that waveform, so that if somebody says, here's a data stream, and I want you to transmit it between this point and that point, and you go, whoa, what's my system? Now that's that channel, and that system may mess with that information. It may shape it weird, but you now know how it's going to impact. If you could find the h of s of that channel, you could find the transfer function of that system. Now you can relate that system's behavior to the frequency content of that waveform or that data stream that you're pushing through that system. Does that make sense? What we now want to do is figure out where those are coming from. That's our goal. And now let me go ahead and see if I can go back to a big size so that I can actually write with my big crayons. Sorry, I thought maybe you were asleep and I needed to wake you up. And so now we need to start coloring. Did everybody bring their pack of 8 colors, crayons, that we can now color? Oh, now it's pretty easy to buy a big box of colors, isn't it? All right, well, how times have changed. Goal. I was happy to just get 8 when I was your age. When I was in kindergarten, when I was your age, I was happy with 8 crayons. All right, now I have your attention, maybe. What's our goal? Now we want for an aperiodic, which just means that this is not periodic, we want to figure out if you're given an x of t that's no longer periodic. If it was periodic, you could find its frequency content by doing some Fourier series analysis. But now what we want to do is find an expression for x of t containing everlasting exponentials. And this is really just the frequency content. We have these exponentials at all frequencies, and they last forever. And we want to know, how do we build up our signal x of t out of such sinusoids? And if we can figure that out, then we know the frequency content in that waveform, little x of t. Suppose you now, here, let me give you the following. Suppose you're given an x of t that maybe looks like this. Maybe it's now that. And you want to know, how is that going to be shaped or modified as it goes through a system? It's not periodic. Is there a way, though, that we can expand or express or write x of t into a collection, which means maybe we want to sum these up, or in the limit, maybe now we're doing integrals. Of complex exponentials. Is there a way that we can rewrite x of t as this integral of exponentials? And that's what I just started with in terms of those equations. So we're trying to derive those equations. Now, can we write it as a convolution? Is that what we want to do? And now what I want you to get comfortable with is doing something like that. It's using what you already know. You know how to do a lot of things. You know how to perform convolution. You know how to write equations that govern a circuit behavior. You know how to find the Laplace transform. You know how to find Fourier series. You know how to find all integrator block diagrams. How are we going to now use what we already know Now I'm asking, what do you already know how to do? What would make this problem more straightforward if I said, find the frequency content of this waveform, and I sketch that waveform x of t? Pardon? We could maybe just make it fit into what we already know. If it's now this little triangular waveform, it's just one. How about if I make it periodic, and it's always a bunch of little triangles? And then I'll figure out, what if I spread those triangles out, and in the limit, maybe I'll have something. That's what I want to do. We know how to answer that question via Chapter 6. Chapter 6 is Fourier series analysis. Can we now do that or apply that somehow indirectly and then make it apply to what we have? What we want to do then is expand or write. This is what we've learned in Chapter 6, where we can expand or write periodic signals into a sum of complex exponentials. And that was the complex exponential Fourier series. What we can do now, this is rhetorical, can we use this information or this knowledge? And what was just suggested is, what if we just created a periodic waveform that looked like that first triangle, except we repeat it with a period of capital T? That's what we want to do. What if we create, or what if we created a periodic signal from x of t? And we're going to call that something special so that we know what we're doing. We'll just say that we are extending that x of t to be periodic, so we'll just call it a periodic extension. We are now interested in the following. That's what we began with. Now we'll just sort of define a period. Let's say this is now t naught over 2, and this is minus t naught over 2. And over here is t, and we'll just make the same thing. Back here is minus t. And notice that we're not having these overlap at all. So this looks the same as long as we keep them separated. Whatever this had for endpoints, we just go a little bit beyond that, and then we say, okay, now you can start copying. So we basically went into the, I don't know, Kinko's, and we said, can you make a copy of this? How many do you want? An infinite number. But it's not a problem with what we have, right? We have paper and pencil. We can make an infinite number of these, can't we? We just have to draw 3 dots. And we have it. Now we have an infinite number of these, and we can't call this x of t anymore. But we can call it x, let's say, sub t naught. Now that's our period that we've created, where it had to go a little bit beyond where we were non-zero and then start over. Okay? Now that we have this periodic waveform, now we can do chapter 6. Now we're comfortable. We can now find the Fourier series for this newly created periodic extension of little x of t. And we're calling that waveform little x sub t sub 0 of t. Now, remind me again how we write that little x sub t sub 0 of t as a complex exponential Fourier series. What's on the right-hand side? If I said express this as a complex exponential Fourier series, what's the expression? I'm using my crayons, aren't I? I'm trying to help you. That's it, right? We're building it up down to sines and cosines. Our sines and cosines we're representing as complex exponentials. And because n is either positive or negative, we're going to be able to get plus and minus these rotating phasors. And in the right way, that gives us sines and cosines because they are exactly opposite. And this is how each of those are weighted. And d sub n could be complex. This is now our formula that comes right to us from chapter 6. And now that's what we need to do. We need to find capital D sub n, and then we would have the frequency content. This is, since we're trying to move on, this is now equation in chapter 7. This is how we would begin chapter 7. Here's the thought process, because you're probably saying, well, wait a minute. That's for the periodic extension of little x of t. That's not x of t. But if you now generate this waveform from minus infinity in time to plus infinity in time, if you wanted x of t and you have little x of t naught of t, can you get one from the other? Can you get x of t, little x of t, from little x sub t sub 0 of t? Or did I say that wrong? Little x sub big T sub 0 of little t. If I gave you that, could you now give me little x of t? Okay, you just have to throw things away, don't you? You just have to start using your eraser, and that could be a virtual eraser. You just have to filter all that time out. Yes? Yes, you could drive t naught to infinity, but that will be later in our development. But for now, once we have t naught, I'm sorry, little x sub t naught of t as a waveform, now it's a pretty straightforward process to just return somebody little x of t. All you have to do is hand them the picture between minus t naught over 2 and plus t naught over 2. You just throw away everything else. You created the periodic extension, but you know what you're really focusing in on is that little piece. And that's the thought. In a real-world setting, we could find equation 7.1 and just neglect the part of x sub t naught of t that lies outside of our time domain region of interest, which is outside of minus t naught over 2 and t naught over 2. Meaning we now have a strategy. You give me an aperiodic signal, I'll make that periodic, and then I'll do the Fourier series on that, and then I'll neglect everything that's not in that fundamental piece. Now, we have a way of finding the Fourier series of little x sub t sub 0. Now we'll think of it in a different way once we get a relationship built up. We'll start making that t naught spread apart. The period get infinitely wide. And then what's left is what we need also. All right, so here is what we have from equation 7.1. 7.1 is now this expression for our Fourier series expansion of little x sub t sub 0, but in that we need to know the d sub n's, and the d sub n's are just 1 over t naught, integral from minus t naught over 2 to t naught over 2, x of t naught of t, e to the minus j in omega naught t dt. And if you want to follow along at home later, that's equation 7.2a. With that, together with the exponentials, you've built little x sub t sub 0 of t. And we can make that equal little x of t by allowing our period to march off to infinity. That's what was suggested. In general, then, we have d sub n is equal to 1 over t sub n, the integral from minus infinity to infinity. It's not our periodic extension now, it's little x of t. We've let t naught go off to infinity in the limits on our integral, and we've now allowed little x sub t naught in the limit to become little x of t. And that's another equation in the book. Now that we have this structure, let's use it. Let's actually define a new function that's somewhat closely related to capital D sub n. Let's define a new function Remember what capital D sub n looks like. Based on this D sub n structure. Here's the new function. Let's just create something called capital X of omega. This is now going to be related to our aperiodic waveform. This we're going to now be this integral from minus infinity to infinity of little x of t, e to the minus j, but now we don't have little n anymore. We don't need it. Let's just make omega a continuous variable, but now we're integrating with respect to time. We're integrating time out. This omega is now this continuous frequency variable. And if we wanted to know what the frequency content was at a particular frequency, we would just evaluate this integral at that frequency. What we're doing, though, in this integral is what's our variable of integration? What are we integrating with respect to? Time. So we're looking at all time. We're looking at the entire time history of x of t. And if we can see all of x of t for all time, we could then figure out what frequencies are in it. That's really what we're doing. We're just saying, give me the entire history of x of t. It's aperiodic, it's not periodic, and I'm going to boil that down so that I can give you the frequency content in that waveform. That's what we're now defining this capital X of omega to be. We're integrating over all time. And that allows us to analyze the frequency content in little x of t. Now we want to manipulate that a little bit. Let's step back, and we're almost chasing our tail, but here's an observation. Suppose that we now have, let's just assume that somebody's handed us this function, capital X of omega. From 0 out to whatever frequency. And now what we want to do is actually say, well, I can't look at everything. Let me just break this up. Let me sort of look at particular frequencies. Maybe I'll call this omega naught. Then this one is 2 omega naught, etc. Here's 3 omega naught, and we just keep going with that process. What are we doing? If somebody now gave us capital X of omega, now we're simply sampling that at a given frequency interval, and we're calling that frequency interval omega naught. Somebody now gives us this frequency function, capital X of omega. Let's just sample it. And if we sample it fine enough, that's probably be sufficient. We now want to sample Now we're not sampling in the time domain, are we? We're sampling in the frequency domain. We're sampling in the frequency space. This new expression that we introduced sort of with the insight from capital D sub n. We're now selecting points in the omega space. What does that do to our expression for capital X? Now we have essentially broken up that frequency variable into little chunks or into little pieces in omega naughts. Now it's not a continuous. Now we're just looking at it at particular spots. And the integral now will replace that omega with n omega naught. We have x of t, e to the minus j, n omega naught t, dt. But that should look very, very familiar. This, if we just had a 1 over t naught, that would be our d sub n. What are we doing? Just chasing our tail? Sort of, but that's what's guiding us. If I now multiplied this integral, or what is that integral equal to? Relative to d sub n. How could I write this in terms of d sub n? T naught times d sub n. This is now just T naught times d sub n. Since d sub n was that integral divided by T naught, that integral becomes T naught times d sub n. Now we have a way of expressing d sub n. D sub n is now this sampled new expression for our frequency, capital X of n omega naught, divided by T naught. Or this is 1 over T naught. It's just a scaling of our sampled value of frequency. And what were these d sub n's? You remember what we called those? What were the capital D sub n's? They were in our complex exponential Fourier series, right? But those were just our coefficients, weren't they? These were our Fourier coefficients. And if I just wanted to say, well, what is capital D sub n, then that's the coefficient for the nth harmonic.